Ok, lo streaming sta partendo. Ok, signori, buongiorno, mi sentite? Posso cominciare?
Professor,
Yes?
can you talk in English, please?
Sorry, yes, sure. Can you hear me? May I start?
Yes, thank you.
Okay. So we shall start. Going back from where we stopped on Tuesday. So we go on with the modeling procedure. And today we'll give a look to three fundamental steps, what are mathematical formulation, sensitivity analysis, calibration. And this gives almost all of the core part of the modeling procedure. So let's talk a little bit about mathematical formalisms. I'm going very quick here because I assume that you already have seen and you know these things from your math classes. But in general, we may say that any dynamical system can be formally represented by the following ordinary differential equation, ODE, also known as the system specification. So we have four sets of differential equation systems. The first one, I hope you know this notation. When I put a dot up here, it means with derivative in time. So I'm talking here about a vector of state of a system that is an n-dimensional vector. It is a vector because I have an underline sign, and it is the derivative, first order derivative in time because I have a dot over it. So this means that the first order derivative of a vector of states or of vectors of state variables, but is, let's assume, an n-dimensional vector, is made equal to a vectorial function f, that is function of the state, of a vector of state variables, the vector of inputs u, the vector of parameters p, and time. Besides this, in order to define the system specification, we need also to introduce the vector of the input, that is a p-dimensional vector, but I may write this way. So this is the vector of the input is equal to a vectorial function z, that is function of the vector of the state variables, the vector of parameters, the vector of inputs, and so on. So the vector of output is a function of the vector of input, the state variables, the parameters, and time again. But in order to conclude the system specification, I need to also include the what we may call the initial conditions. So we write that the vector of state variables at time 0, at first time instant which my description starts, is equal to a vector of values, that is the initial vectors, so of the system specification. Besides these three vectorial ordinary differential equation, I may also introduce a fourth element. Again, it is a vectorial function in which I try to include all the practical limitation on the state variables and on the parameters. So typically in this kind of description, what I include is, for example, that the entropy shall grow, or that the energy shall be conserved, or that the space or the let's say space or mass may be conserved, and so on. So these these inequalities, or this last function, again, it is a vectorial function, that is inequalities, meaning that this is a limitation, describes the limitation, practical limitation or physical limitation of my system specifications. So we may say that equation 1 to 4 depict a very wide range of system behavior in a deterministic way. So by writing this, I am assuming to be deterministic. Of course, we know that uncertainty is an intrinsic component of any ecological model, so we can use vector of stochastic processes in order to include some kind of stochasticity or randomness into the model, but of course, in this case, things get very complicated. In general, we use, and these are rules of thumbs, but we shall employ always. In general, we use first-order kinetics. This means first-order time derivatives, linear function where possible, and autonomous systems, so systems that are independent of time, in which the explicit function here do not depend on time. Of course, this is not always satisfactory, but the problem is that the analytical tractability of nonlinear ordinary differential equation is very limited. For not too complex situation, maybe I may employ also numerical approximation techniques. And this is a must when I start having quite complicated systems of non-linear ordinary differential equation when I resort to numerical approximation, numerical solution. But this, of course, you can imagine from one side requires a large cumbersome, a large load of CPU time, and also requires also accepting very large or strong approximation in my description. I may formalize these again by depicting a system by drawing a boundary. Inputs that are measured are what we have called up to now forcing function, a vector of inputs attacked on the state, changing the system state, what is described by the vector of state variables, and then the output, what is again measured, what is the results of the solution of my systems of ordinary differential equation. In general, we may make this simplification or with this schematization. We distinguish from an inside, we distinguish between an inside and an outside, and the interaction between inside and outside are mediated through this vectorial function, u and epsilon, function of time. But I may include some stochasticity by considering some kind of stochastic perturbation that may change in a more or less random way the values of the state variables of the vector of state variables. So in general, we may, this is a matter of notation, we may convert ordinary differential equation by algebraic calculation. By, for example, I move this function on the other side, so changing the sign, this may become x vector derivative first order of x vector of the vector of state minus the vectorial function f is equal to 0. And this is a customary way in which I may represent my ordinary differential equation. So my ordinary differential equation may be seen as a function of the state variable, of the input of the first derivative, second derivative, nth derivative of the input, and this is equal to 0. Typically, the solution of this system may be written as epsilon equal to a vector, a function g of a vector of state variable x, this is the general solution, but by employing the third element here, initial values of the state variables, I can find a particular solution of the ordinary differential equation, and then I obtain that the particular solution is equal to epsilon equal g, a function vector, a function of a state variable vector plus a constant. This is a particular solution. We've soon seen some example of this. In particular, let's be very practical. Let's think Let's focus our attention on, for example, a bacteria colony. We may introduce the state variable mt representing the number of bacteria time t in a chemostat. So we are assuming steady state condition. Chemostat means that the chemical physical conditions are maintained constant. At each time interval, let's say delta t is the time needed for bacteria to grow. So the time needed, you may recall that bacteria grow by splitting in two. So each delta t, we have a splitting, so that at n t plus delta t, we will have a number nt of bacteria plus a number that is proportional to the number of bacteria that may split through a couple of constants, alpha, that is called typically the intrinsic growth rate of a system, and delta t, that is the time interval considered. So the larger delta t, the larger will be the number of bacteria that are blown into my system. If we make delta t tend to 0, you may recall from your first mathematical classes, this is exactly the definition of limit. And in this case, we obtain that the derivative in time of the number of bacteria time t is equal to constant or parameter alpha times the number of bacteria time t itself. So we have, this is the first order ordinary differential equation describing bacterial growth. And alpha is the parameter that is customary called intrinsic growth rate. So you see that by employing these formulas we have introduced here with all these assumptions, we end up with a solution, have the first order ordinary differential equation, and this solution is very trivial, which is the only function in mathematics whose first order derivative is equal to itself. But the answer is it is the exponential function. So the first order differential equation, that is a very general approach, may have a solution, but in its general form says that the derivative in time t of the state variable vector x is equal to a function of a parameter that is dependent on time, at times the state variable plus the particular solution. So we have the general solution by integration. This is the general solution of the first order derivative differential equation. And we may have particular cases, just to start looking what this function looks like. If beta bt is equal to 0, so this is the general solution, then it is xt is equal to the integral of at. And if bt is equal to 0 and at is constant, we end up with a very customary, well-known exponential function that is the classical solution of this differential equation. So this differential equation, prototypical differential equation, what we have obtained by trying to describe what is happening into a chemostat in which a colony of bacteria grow. So we simply write that at time t plus delta t, and delta t is the time needed for this bacteria to split. We will have that the number of bacteria is equal to initial number plus a constant that is the intrinsic growth rate representing the speed at which bacteria grows times the time in time interval. Then we end up with this first order differential with first order ordinary differential equation describing bacterial growth whose solution in the general solution is described by these forms, general form and general solution is this form, plus the particular solution, and then we end up with an exponential growth function in time. So our first example of first order differential equation ends up with an exponential function as a solution. Okay, this methodology, that is quite general, may be recasted into more general theoretical principles. In particular, we may subdivide the contribution of grow processes into my chemostat into two gross categories: exogenous and production. Exogenous factors are factors related to the interaction of my system with the external environment. Exogenous factors may be described by what is going in minus what is going out from my chemostat, plus a term that we may call production, and this term may be subdivided into two subterms: formation of a product minus transformation of a given product into something else. So you see, you have both the two categories, exogenous and endogenous or production. Exogenous means interaction with the external environment, and production means processes that are internal, endogenous to the system. We may write the differential equation, the first order differential equation, by writing that the derivative in time, so the change in time of a number of elements into my system. I recall you that we have starting this reasoning by thinking at a chemostat with a bacterial colony growing. This variation in time of a number of elements into my constant is equal to what goes in minus what goes out, plus what is formed minus what is transformed in something else. This way of writing the time variation or the effect of endogenous exogenous processes onto a population of something is a very, very general formalization of what we know as the energy conservation principle. So if we assume the energy conservation principle, and we do assume it because we believe in the first principle of thermodynamics, then we may translate all the processes of transformation of a population into what is called a continuity equation, in which I assume that the variation in times of the state variable describing the number of elements in my system is equal to what goes in minus what goes out, plus what is formed minus transformed. In the case of the bacteria population that we have seen in the beginning, we rewrite this this equation, variation in time of a number of bacteria, by writing that the variation in time of a number of bacteria is equal to a positive term that is, of course, proportional to the number of bacteria itself, because I recall you that bacteria, simple organisms, we may think that grow by splitting. So, of course, growth rate is the constant that describes the increase of a colony in terms of splittings, so in terms of what it was present, minus a negative decreasing limiting term. In this way, we may write it by saying that the variation in time of a number of bacteria at time t is equal to a constant R, that is typically the intrinsic growth rate of a population, multiplied by NT, and I'm here collecting NT, and I'm here making M dependent on the number of bacteria itself by a square function, by explicitating the intrinsic growth rate alpha as a function of a number of elements divided by a limit number that is called the carrying capacity of the system. As n tends to n0, you see that alpha growth rate stops. So this is a first example of a non-linear ordinary differential equation that describe the growth of a population of bacteria in which something happens to limit the growth. So these bacteria cannot grow indefinitely. I already told you that unlimited growth is ecological nonsense. This is why we recast the continuity equation by writing a term of positive increase of the number of bacteria, but we also include a negative limiting terms that we may call M because it is very similar to what ecologists call mortality, and may be made dependent on the number of bacteria itself, representing the fact that as the population increases, the resources for the elements of a population are becoming to be limited, and this is the effect that slows growth. And what we obtain by this first example of non-linear ordinary differential equation is the classical equation of the logistic growth. And we will see this equation appearing here and there several times during the class. It is really prototypical because it is the first example we may recognize of that describes a process of limited growth. Unlimited growth is ecological nonsense. Limited growth is a way of describing growth, including limiting effects like mortality effects due to the fact that the population, as the population increases, the resources become limited. And in order to describe this, we shall employ a second order, non-linear, sorry, a first order, because these are derivatives of the first order in time, non-linear because here we have an n square, ordinary differential equation. We may see several examples of this description in ecological systems. In particular, there are several relationships that are called in general allometric relationship that allows us to find connections between the speed of growth that is represented by these parameters R and the characteristics of organisms. For example, if we make a plot of length versus generation time of various organisms, here we have that if we display this plot log-log graph, we have that all these points are distributed in log-log line. In particular, here we go from several order of magnitude, 1 hour to 100 of years. So 1 hour, so we are talking about bacteria. 1 day, we are talking about larger animals. 1 week, months, we are going to mammals. 1 year, 10 years, we are going to large plants. 100 years, we are going to very large plants. So we are covering 1, 2, 3, 4, 5, 6 order of magnitude of length generation time. So this is the time needed for an organism to reproduce itself. And if we plot a typical dimensional indication of this organism, but maybe, for example, the length or one of the length, we go from micrometers to millimeters to centimeters up to hundreds of meters. And we see that all these dots that represent the whole realm of living objects, going from plants, going from small bacteria up to enormous oak plants, they all display on a in a log-log plot along a line. This is very relevant when we need to find the values of the various parameters describing my growth model. Now let's introduce some of the steps that allows us to understand how or to characterize the behavior of my model. In particular, the first step, but the model should apply after mathematical formalization, is that of doing sensitivity analysis. What is the purpose of this analysis? Sensitivity analysis is oriented at identifying the most sensitive components of a model. For example, you may try parameters or forcing function or even part of a models that we may call submodels, and try to evaluate how much these elements change the performance of my model. In particular, how much, for example, changing in parameters or forcing functions may have an effect on the state variable. In order to evaluate how changing parameters, forcing function, or the characteristics of model change the state behavior of a system, we may employ the condition number, also called sensitivity. Condition numbers or sensitivities are derivatives normalized on the absolute value. So how much the variation, for example, of a parameter, the p, in a relative variation compared to the relative variation of the state variable x, and this number is called the condition number that describes us how much the various elements of the model may modify the behavior of the model. In a certain way, we may say that condition numbers measures the sensitivity of a variable x to a parameter p. So we have several condition numbers, and we have at least some same number of condition numbers, but is the combination between state variables and parameters. Typically, we investigate at least two levels of variation, for example, plus minus 30% of the parameters or plus minus 60% of parameters. And this is important in order to help us in deciding which are the parameters are the most sensitive, so those that more significantly change the behavior of the model, and that need to be determined more accurately in order to start the calibration procedure, as we will see soon. It may happen that in certain conditions you may investigate further levels of variation of particular parameters, in particular those parameters that are most sensitive. Please remember that sensitivity analysis is a fundamental prerequisite in order to proceed with the calibration step, what is the next step. Sensitivity analysis, you start studying the behavior of your model that you have obtained, for example, by various assumptions on the growth of bacteria or the growth of the element appearing to your system. The fundamental assumption, I recall you, is the energy conservation, energy/matter conservation, that we formalize into a continuity equation, that is the equation that we have written here. That is a tentative, it is a way of trying to including all the aspects, positive and limiting, negative limiting aspects of processes like such as growth, by studying allometric relationship, for example, between generation times and particular elements characterizing your organisms, for example, the length of the bacteria into your chemostat. Then you end up with a formulation of a model, and then you start trying to analyze, study the behavior of a model in terms of sensitivity analysis. The change applied to the parameter shall be consistent with uncertainty associated with the parameter. Of course, if the parameter I am looking at, for example, settling velocity of algae, is known with a limited with a defined uncertainty, it is useless, but I make a sensitivity analysis with variations that are smaller than the uncertainty of a parameter. It is important to note that the sensitivity of the various state variables or parameter varies over time. And it is important also to note that we may be interested in studying the sensitivity of some models in terms of structural changes. Some models are fundamentals when you want to include evolutive processes, so that, for example, take into account structural changes of the system. So, for example, appearance of new species over disappearance of extinction of some other species, or the appearance of new processes. For example, some animals or some organisms change their diet and start consuming substances from different sources. These are all structural changes that shall be analyzed, for example, by analyzing the sensitivity of some models. In general, you start your sensitivity analysis once you have your conceptual diagram defined, so the level of complexity, or if you want, the hierarchical level of your description is defined. And there are some statements that have to be taken into consideration. For example, some models containing sensitive parameters are generally sensitive to the main state variables. That means that if a sub-model contains a parameter that is sensitive, then the sub-models itself is sensitive to the main state variables. The reverse, it is not also always true. Some models that are susceptible to major state variables may not necessarily contain sensitive parameters. That means that sub-models may somehow buffer or absorb the changes or the effect of variation of the parameters that appears into the sub-model. And I give you in this table an example of first sensitivity analysis. This is a model describing interaction between phytoplankton and zooplankton. The currency here is soluble nitrogen and soluble phosphorus. We look at annual average values of the sensitivities that are plotted in this table. For example, these are the various parameters: max growth rate of phytoplankton, the nitrification rate, or initial zooplankton concentration, rate of mineralization. So these are all parameters that describe ecological processes that I chosen to include into my model. The parameter has a definition, but is this one. Then the sensitivity analysis, so this is the sensitivity, for example, of the variable phytoplankton, of the sensitivity of the state variable zooplankton, of the sensitivity of the state variable soluble nitrogen, and so on, or soluble phosphorus, and so on. These are calculated according, evaluated onto the effect compared to the effect of variation of various parameters, and you discover, for example, that the rate of mineralization, the max growth rate of phytoplankton is significantly sensitive to the concentration of the zooplankton. This is due to the fact that zooplankton in your model, in our model here, is feeding on phytoplankton. So a large number of phytoplankton, of zooplankton eating phytoplankton, act onto the population of phytoplankton by changing or lowering the maximum growth rate of the population. Again, the max growth rate of zooplankton in this case is terribly sensitive to phytoplankton. You see the condition number for phytoplankton is very high. The condition number for interaction of zooplankton is very high, of course, So the maximum growth rate of zooplankton is dramatically changing the behavior of the model in terms of concentration of zooplankton and phytoplankton. These kind of analyses are important if you want to make a ranking of what parameters are more sensitive, which are the most sensitive parameters, because as I told you, when you start calibration, you shall initiate your calibration by calibrating the more sensitive parameters. This is another example. These are condition numbers. So these numbers S plotted for the various elements of a model. This is a model of the quality, water quality in the river, the canals of the city of Venice. Here we have a set of parameters, but also we have made a sensitivity analysis and also on two external conditions, like for example, loads of CBOD or ammonia or organic nitrogen and so on. And also we have made a sensitivity analysis of a boundary condition. The variables are dissolved oxygen, CBOD, ammonia, and nitrate and organic nitrogen. So 1, 2, 3, 4, 5 state variables, and you look by this analysis, you discover immediately that, for example, the NH3 state variable is dramatically sensitive to the T71 parameter. That is the parameter I tell you linked to the, this is the Arrhenius constant of the mineralization process for ammonia. And of course, it is evident that the state variable ammonia is terribly very sensitive to the parameter, to the Arrhenius parameter of mineralization of nitrogen. I told you already that sensitivity and a function of time. So in general, you may also find useful to study how sensitivities varies in time. In particular, here we have a plot, two plots, in which we plot the dotted lines here are substrates, while the continuous lines are describe population. So this is the substrate and related sensitivity. So we have a substrate with a population, let's think bacteria, that is growing by consuming a substrate that is food for the bacteria. Bacteria are feeding on the substrate. We are studying the sensitivity of various of the substrate, the sensitivities of various parameters appearing to my model in time, and we see that as the substrate get consumed, meaning that the population is growing, we have increasing sensibility onto some parameters, we have decreasing sensibility. In particular, this is the sensibility onto the internal growth rate. This means that as the substrate decreases in time, the sensitivity to a parameter growth rate of a variable phytoplankton, or the variable describing the population, is decreasing dramatically. This means that as the substrate decreases, we have a quicker and quicker slowing of growth of the population. We have a symmetric, we have a symmetric story here in which we depict the biomass. So while here we were studying the substrate, how the substrate will consume, here we are studying how biomass increases. So here we plot the sensitivities of various, the sensitivity of biomass to the various parameters. In particular, here is the sensitivity to the growth rate mu, as the biomass increases, the sensitivity grows, and then once the substrate is consumed, so the substrate is finished, this means the population starts to die, then the sensitivity of the growth rate tends to decrease as well. So this is more or less what we need to know in order to proceed to sensitivity analysis. The step further after sensitivity analysis is calibration. Calibration means estimating the ecological parameters in order to make the behavior of my model the more adherent to my observation, to experimental observation of the system I want to describe. We have to start by realizing that in general, parameters do not have exact values, instead they change their values, or they are known with a certain level of certainty. We may keep in mind the fact that simplified models are that my model, we may take into account that my model is a simplification of my description. So the parameters that may appear in the model for calibration may not be real parameters of the parameters of the actual or real or experimental system, because we are employing simplification of the description. When we have to take into account that in certain conditions we have aggregated parameters models in which you have, for example, you are including to the parameter the spatial variability of the system. So maybe some parameters may change their values in different places of the system. So if my system, the system I want to describe, is a system that may be differentiated in space, when you do an aggregated parameters approach modeling, then you are including all the variability of a single parameters into of the variability due to the spatial heterogeneity of a single parameter into one single parameter, and this makes this entrains the fact that the parameters are not always representing real conditions. And then you have to take into account that ecological systems are quite flexible, so they may display some effects like structural dynamics linked to the fact that the living system may tend to evolve. Parameters are sensitive or affected by environmental factors as well, are iterative and subject to feedbacks. This means that there may be several interactions that are not always explicit, so that may change or may act in a dramatic way in changing the effect of parameters. Parameters can be determined directly, for example, the example of allometric relationships between lengths, generation length, and dimensions we have seen before, with typically an allometric relationship, but as we will see soon, we may employ to calibrate the model. But there are also some way of determine the parameter indirectly by, for example, studying reaction times or chemical composition or the energy contents of the products. To find the parameter values, we start generally by a first guess from the literature. We have a very important publication, that is the Handbook of Ecological Parameters of Uncle Sven Erik Jorgensen, which collects an enormous amount of parameters that you may find in literature, in ecological modeling literature, in which, so you have an indication of which values you may choose in the beginning. a first guess. Then you may decide to be more refined. So, for example, you may establish in situ process analysis, or you may decide to implement additional experimental measurements, and you shall always verify that the timing is appropriate to capture the variability of the system. This means that um, when you collect experimental data in order to evaluate the behavior in terms of calibration of your model, you shall be sure, or you shall verify that the variability, time variability of your system um, or is appropriate or is appropriately described by the variability, time variability of a parameter that you are implementing to the system. This is an extract of the handbook of ecological parameters of Sven-Erik Jorgensen. Here you have a table in which you have, for example, algal types, so which algae I'm working on. And for example, the parameter, here you have a complete set, a very large set of values, setting velocities for different algal type. So for example, if the algal type is total phytoplankton, you may employ one of these values, of these ranges, and Sven-Erik Jorgensen has provided also the references. So you may read the paper in order to understand if the parameter that you're choosing for your system is consistent as the same meaning we are describing, the same system and so on. For example, you may change here diatoms is another type of algae for which you have different values of setting velocity with different references, green algae or blue-green or flagellates and so on. You see that, for example, the settling velocity of flagellates as expressed by Liebman here. Liebman here is quite high compared, for example, to the settling velocity of blue-green algae, at least in the first paper. And if you go and read the paper, you shall understand why the modelers have find with different values, very different values of parameters. So you see the range of variability of parameters is enormous. And this way, we try to find papers in which scientific papers published in literature in which there are studies of the systems similar to the one that I'm working on, and look for indication of the various value of the parameters included to these descriptions. Another example of how to employ allometric relationships for calibration. Give you a first example of an holistic description of a quite complex process like fish growth. In this case, we may write, and this is another way of casting the continuity equation or energy conservation principle. We may say that growth or anabolism is equal to the variation in time of metabolism. So the variation in time, sorry, the growth or the variation in time of the weight of the animal. And here I'm thinking at fishes because we will see a metabolic growth model explicitly focused on describing the dynamic of fishing. Then we may write that variation in time of the weight of a fish may be made equal to two terms, a positive term of metabolism and a negative term of catabolism. Metabolism is the energy consumption per unit time per unit body, per unit of body biomass, minus catabolism, that is the energy employed by a starving organisms, so the energy employed just for maintaining the organism alive. So we may subdivide the total energy consumption, metabolism, into two contribution, growth, that is anabolism, plus catabolism, that is the energy employed by the organism to survive. If we will look at how feed is transported to an animal, a large animal, like I'm thinking a fish, we may say that fish body is body, again, border inside, the body outside, body, the fish feeds on food, and then this food is transformed into various energy flows. We have respiration, non-digested food, that is food that is lost during the process of digestion. This is assimilation, assimilated food, non-utilized food, so this is food that is lost during the process of assimilation. What it remains, it is growth. If we indicate with W the weight of the fish, we may write that the variation in time of growth, the variation in time of biomass, of the mass of the animal, is equal to a general exponential model in which we employ two parameters, A and B, and the model is somehow proportional to the weight of the animal. So here we have a first order non-linear or linear differential equation. Non-linear because, of course, there is an exponent onto a state variable weight of the fish. Then, if you include consideration about the energy obtained by digestion in particular in terms of the composition of the food, we may say that 9% is proportional to the fat content of food, while 4% is proportional to the carbohydrates plus protein content of the food. By this kind of consideration, you may find allometric relationships that link, for example, with another example of a log-log plot in which I'm linking the weight of the animal to the consumption in terms of metabolism, energy consumption of the animal. So we write what metabolism is equal to anabolism plus catabolism. So the totality of the energy flow in the animal is linked to what it goes to growth plus what it is employed for surviving. So this is a simple function of the weight. Then you find a allometric relationship that allows you to plot on two linear lines very different organisms pertaining to very different dimensional spaces. In particular, here we have the logarithm of a weight. So we are talking, these are exponent of a weight. As if you are talking about grams, here we go 10 to the minus 4 grams to 10 to the 4 grams. So we are talking about larger, very larger animals. All these animals, these parameters, are found on a line. And this allows you, for example, trivially, if you convert these, if you recall how we have defined the growth model, in a log-log plot, finding the slope of these lines allows you to find, for example, values of the parameters A. Another important things to note is that we may subdivide the organisms, for example, according to the way they use energy. Homeotherms, like we are organisms that tend to maintain internal temperature. So, of course, to the same weight, homeotherm has a larger consumption in terms of metabolic energy. Heterotherms instead are animals or living objects, but whose temperature varies according to the variation of external environmental temperature, and unicellular or algae are in general both organisms or living objects that whose relationship between the weight and the energy consumption is lower. We may find several allometric relationships in several fields that are of relevance for the environmental engineer. In particular, here we have concentration factor for cadmium versus dimension of the animal. Again, you know that concentration factor are the factors appearing in the BCF models, but I'm sure you have seen in ecotoxicology. And in this case, you may find that concentration factors for very different in size organisms or display on a log line. On a line here we have goldfish, one, a larger animal, mussels, shrimps, zooplankton, so we are talking of very small animals, and algae, number 5. These are brown-green algae. All these organisms, in terms of concentration factors, may be found on a line. So this tells you that if you take a log plot of this, you know that if you make a log here, you will have A plus B multiply log weight. So this becomes a line in which B is the slope of B is the slope of a line, and A is the intercept of a line onto the horizontal axis. In this case, by employing this kind of relationships, you might, for example, once known the dimension of the animal, you may have a first guess what may be the parameter concentration factor. There is another way of estimating the initial value of parameters for your model. We have similar case, for example, this is uptake rate, microgram per gram every 24 hours of cadmium plotted against the length of various animals. Here again, we go from phytoplankton to clams to oysters, so very different animals, but again, in a log plot, you find that the values are found on a line, and being able to identify these lines allows you to, for example, by measuring the size of the animals, have a first guess or first estimate of what may be the uptake rate of cadmium of this animal. The scientific, ecological, environmental engineering literature is plenty of this example. This is the same story related to DDT and PCB, excretion of PCB and DDT versus organism size. Again, sizes of the organism and the rates of excretion. So again, you have if you know if you are able to describe this line, then you can easily pass from the dimension of the organism down to the estimation of the various parameters, in this case, the uptake rate every 24 hours. Okay, give me 5 more minutes and we finish. We shall also include here some methodologies for the evaluation of the behavior of a model. Objective of a model is to be able to reproduce reality. Values of state variables that are calculated by the model shall be made as similar as possible to these observed in nature. So, calculated by the model shall be made the most close to observed in nature. There are essentially 3 general ways of making this kind of evaluation for assessing the goodness of a model: visual techniques, measurement of deviation, and various statistical tests. These are an example of visual techniques. This is a nutrient generation model in a large river basin, in the Po River. We will have an entire lecture on this model. And we see that P, we are talking about phosphorus, the currency here is phosphorus, so the plot is total phosphorus along the main run of the river Po. And we plot these measured values of phosphorus, and being on the pink line, instead we are trying to calculate by a model to calculate the concentration, calculate the nutrient loads in terms of phosphorus along the main river. One way is that of simply trivially plotting measured values against the performance of a model. And another way is that of plotting on one-to-one plots. For example, here we compare dissolved inorganic nitrogen loads as measured with dissolved inorganic loads calculated by the model. What we observe that, especially in the lower part, the lower concentration range, the model is performing quite well, quite bad, meaning that when instead we go to the higher concentrations or higher loads range, the model is going quite well. And when we go into the detail of the model, we will give an explanation of this behavior. The largest the subbasins, the better the model works. So the better the one-to-one relationship. And in terms of model evaluation, we may employ automatic algorithms, the types of algorithms that you may find in MATLAB. It's called calibrator. I think in MATLAB there are some modules that allow you to reduce the distance between the performance of a model and the experimental data. So the idea is that of finding the minimum of some measure of distance. Typically, you may use the simplex method that you may have seen in statistical analysis, or you may employ very classical statistical measures of deviation, like the mean absolute error, or the mean absolute percentage error, the root mean square error, and so on. But I have to tell you that by far the most employed measure of deviation is the so-called efficiency, or the Nash and Sutcliffe coefficient, in which we simply make a ratio by comparing the differences between simulated values, observed values. So these simulated values, and these are observed values, and these are observed values and average the simulated values. The usefulness, so this is the average of the observed values. The usefulness of this efficiency tells you how much you are doing better when employing the average. So if my model produces simulated values like this one, epsilon tilde here, when I compare it with the use of the average, if the Nash and Sutcliffe coefficient is smaller than 0, meaning that this ratio is bigger than 1, this means that by employing the average of our observation, I would do a better job than by employing a complicated mathematical model for producing this calculated value. The efficiency, Nash and Sutcliffe efficiency, is similar to the regression coefficient R squared, what you may find, for example, in Excel. It does not have a defined a priori distribution, but is by far, as it anticipated, the most used tool for evaluating the performance of a model. we stop here today, and we will start back next week, finishing the modeling procedure and going into the ecological processes sectors. Okay.
Thank you. Bye.
Bye bye. Stay in the class for some minutes. Zampini, se vuole, io l'aspetto qui adesso.
Sì, sì, va bene.